All right, this is Coach Williams, and we're going to work on 6.3 and 6.4 notes today. This is going to be dealing with exponential functions. Before we get into the types of functions, being, growing, getting larger, growth functions, or decay functions, we kind of need to know what the exponential function is itself. And an exponential function is simply this. It's a function. Let's write this down. It is a function that increases, increases or decreases in value. And you could say this is the f of x or y value, okay, exponentially. Okay, it's a function that is increasing or decreasing exponentially. The value, the f of x value or the y value, is increasing or decreasing exponentially. And the function that we look at here, just kind of as an example here, you'll see it written also in our illustration below here. But the function is going to be y equal to a times b raised to the x power. All right? And that also is where, okay, a is not equal to 0. If a equals 0, then the whole thing becomes 0 on the right side, and y equals 0 is not increasing or decreasing, it's staying the same. So that is not an exponential function. It's also, another criteria is that b cannot be a 1. If b equals a 1, and we raise b to any power, raise b to the second power, to the fourth power, to the 56th power, it doesn't really matter. That means that b to whatever power will always be a 1, because 1 raised to any power is 1. And then a, whatever constant out front is, multiplied times 1 will still just be a constant. So y equals a constant is still just a horizontal line at that constant. And so it can't be 0, it can't be 1, and we're looking for this to be when b is greater than 0. In some cases here, you may have b greater than 0, b less than 1, b greater than 1, but it can't be 1, and it has to be greater than 0. So then when these criteria are met, we see a function that's increasing or decreasing in value exponentially. And we say exponentially, we're meaning that it's not changing at a constant rate, or there's not a constant rate of change. And we know that if we have a constant rate of change, we have what kind of function or graph? It has a constant rate of change, it is linear. Linear equations have constant rate of changes, or they have slopes. And you'll notice that we're going to refer back to some of our previous learning where we look at a table and we find the slope or we find the rate of change, and we determine whether or not it is a linear rate of change, a linear function from the rate of change, or if it's an exponential function from the rate of change. The next vocabulary term we have here is asymptote. And an asymptote is simply a line. It is a line that a graph approaches but never touches. Right? It's a line that a graph approaches but never touches. And we're going to see examples of that here in our illustration, where in this case the x-axis is an asymptote. And what that means is that this graph is going to get extremely close to the x-axis but never actually be the x-axis. Now, for it to be on the x-axis, the y value would have to be 0. And so what you're looking at here is this value is going to get extremely close to 0. It's going to be 0.0000001. And then the next time you look, it's getting a little closer, it's 0.00000000001. And the next time it's going to be, as you know, you always make Siri do the, you know, the little beatboxing thing. It's 0.0000000000001. All right, and so, but it's never going to actually be 0. It's just going to be, you know, getting closer and closer to 1 or to the 0 value, but never actually be 0. All right, so that is what an asymptote is. It's whenever a line, it's a line that the graph is approaching, but never actually reaches or touches. Okay. On the illustration here, you're going to see some of those things that we just wrote up here. But you're also going to see demonstration of certain conditions. When b is greater than 1, okay, when b is greater than 1, your graphs are going to look like this right here, okay? On the top side is when a is greater than 0. On the bottom, it's when a is less than 0. So when b is greater than 1 and a is greater than 0, your graph is going to have this look to it. And if your graph is down here like this, it's because your b is greater than 1 and your a is less than 0. And then obviously here this demonstrates whenever b is between 0 and 1 and you have an a greater than 0 or an a less than 0 here. Okay, so those are just some illustrations of different conditions that you can have with exponential functions. All right, let's look at the extra practice. And another, while we're moving along to that section here, I like to make this analogy that kind of helps you understand things expanding or things growing exponentially or maybe decreasing exponentially. And we talked a little bit in class already about a savings account or maybe an investment of some kind. And I know this is not the real world. If it were, then we would all be rich, but or somebody would not be rich because they'd be giving us a whole lot of their money. But if you had a savings account where you gained, and we'll just, like I said, we'll make this non-realistic, but to give you a real quick understanding of the concept, you put in $100 into your savings account, and every year you get 25% interest. You're not going to get that, by the way, but if you were to get 25% interest after the first year, how much would be in your savings account? It would be your original $100, and then we're going to add 25% of that to it. So you would have $125. And the common answer is, okay, what's going to happen the second year? How much are you going to have in there? And the common answer is 150. But it's not 150 because we're not increasing at a constant rate of change every year by $25. We're increasing by 25%. So the first year you have $125 at the end of that year, but the next year you're taking 25% of $125. So it's not $25 anymore, it's $30-something. And so now you add $30-something to your $125, and now your total is $150-something. And the next year you're taking 25% of $150. So you're not, and so then that year, 25% of $150 is going to be $70, you know, roughly. We'll just, or no, it's, I don't know what it is. It's going to be $40-something. And so you're not increasing by 25. The first year's 25. The next year's 30-something. The next year's 40-something. The next year's 50-something or 60-something. And so you're not just increasing by a constant rate. You're increasing exponentially, okay? Because you're taking a percentage of what you had in there from before. So that's exponential growth and an exponential function. If we were to say, okay, you're going to get $25 a year, no matter what your total is inside there, that would just be a linear function, whatever you had, plus the $25 times however many years you get, and you have a linear function. But exponential is when you take the percentage of something or you raise something to a power. So, okay, we mentioned tables, and this is what we're going to deal with here when we're talking about determining if it's a linear or an exponential function. We're looking for a constant rate of change or not. So in this case, let's look at the change in x. What is the change in x as we move down the table? From 1 to 2, we have a change of 1. 1 to 2. And then from 2 to 3, we have another change of 1. From 3 to 4, we have a change of 1. On the y side, we're changing between the y values. From 8 to 4, we're going in the negative direction here. We're going down 4. On the next one, from 4 to 2, we're going down -2. And from 2 to 1, we're going down -1. Is this a constant rate of change? No. If we look at the change in y over the change in x, which is our slope or rate of change in y over change in x, the first one is -4 over 1. The next one is -2 over 1. And the next one's -1 over 1. And those are not equal. So there is no constant rate of change here. So this graph, or this function, is going to be an exponential function. And the reason, or the explanation, is that there is no constant rate of change. Okay, there is no constant rate of change. All right, so this one is exponential function because there's no constant rate of change. Let's look at the second one. From 1 to 2, from 2 to 3, and from 3 to 4, we're going to have 1 again for all of our changes in x. This is kind of making it easy. On the next one, 3 to 7, 7 to 11, 11 to 15, the change in the y values, we're increasing by 4, and then we're increasing by 4, and then we're increasing by 4 again. So my change in y over the change in x is 4 over 1, right? And it's the same. They're all 4 over 1. So my constant, it's a constant rate of change, and because it is a constant rate of change, this one is going to be linear. This is a linear function. A linear function, and the reasoning is because we do have a constant rate of change. And we determined that was 4 over 1, or just 4. Okay, for number 3, again, our changes in x are all 1s. Our changes in y's, we have a -3, a -3, and a -3 again. Correct? So everything here is the same. Constant rate of change again. Our change in y over the change in x is equal to -3 over 1. Okay? And since we have this constant rate of change, once again, this is going to be a linear function. Linear function. And same reason we had before. Constant rate of change. Okay, last example in this group here. We're going to have, once again, changes in x's are all going to be by 1. The changes in y are not going to be constant. You can already tell that just from the size of the numbers here. The first one changes in a positive direction by 0.375. This one changes by 1.5, and this one changes by 6. Is that constant? No. No. There is the change in y over the change in x is not constant. We have 3 different rates of change between value values in x. The y value does not change in a consistent manner. So this one is going to be an exponential function. It's an exponential function because there is no constant rate of change. Okay, let's move along. On to the next practices or examples for this section 6.3. We are asked to evaluate the function for the given value of x. And in this case, we have learned already about powers just previously. So y is going to be equal to 3 raised to the power of x, which x equals 5. So we put raised to the power of 5. When we put this in our calculator, we end up getting a value of 243. And so, that's easy. Nothing more to be done here. We just raise 3 to the power of 5. We get 243. And that's our answer. That's it. On number 6, same thing. Y is going to be equal to 1/4. 1/4 raised to the power of 3. Now we learned in our previous sections for chapter 6 that we can just apply this power to the 1, we can apply this power to the 4, and anything, or any 1, any 1 raised to any power is just going to be 1. So this is actually the same thing as y equal to 1/4 to the 3. We don't have to put the power on the 1, it's just going to remain a 1. And 4 to the 3rd power is the same thing as 1/64. 4 times 4 is 16, and then 16 times 4 will be 64. So 1/64 is your answer. The question was asked, do we have to put the 1/4 in parentheses? If they put it in parentheses, you need to put it in parentheses. If they don't specify parentheses, then you don't have to worry about it. In this case here, they put it in parentheses, and so we know that we're going to take the whole thing to the 3rd power, which you could do that in one step on the calculator, or you could apply the rule that we have, the property we have that says, well, that just means I can take 1 to the 3rd power, and we could write it in if we wanted to, over 4 to the 3rd power, meaning we apply that power to all the terms in the parentheses, and then we can carry out, the rest of our PEMDAS and work out the exponent values and solve. So, okay, number 7. This one we're going to have y is equal to 3 times 4 in parentheses raised to the x value or x value of 4. And again, we mentioned it just now, but PEMDAS says we do parentheses, then exponents. So we have to take 4 to the 4th power before you can multiply 3 times 4. If you multiply 3 times 4, then raise it to the 4th power, you're going to end up with a different answer. All right, so y equals 3 times, what is 4 raised to the 4th power? 256. And then we take 3 times that, and we get 768. Okay? So 768 would be the answer on number 7. Okay, moving on to graphing. And the graphing part, we're going to use our calculators to help us out tremendously. The first thing I'm going to tell you to do is to put this in the calculator in the y equals to give us an idea what this graph is going to look like. And then we can look at the table to find actual values for this graph, and we can plot those points and draw it ourselves. Now, if you go to y equals on your calculator, you can put in -2 raised to the power of x. Now, in this case, they do not specify the parentheses around the -2, so we're not either. When we put that in, that's our function. We can go look at the graph, and we will see it graphed on our screen and give us a pretty good idea of what the graph is going to look like. But more importantly, what we can do now is we can go second graph, and it gives us table values. And I want you to actually create a table on the side of your graph here. You're going to have your x and your y value or your f of x value. It doesn't matter. They're the same thing. And just pick about 3 or 4 values and plot those points on the graph. And I'm going to tell you the most important thing here is to pick the values just a little bit before 0 and a little bit after 0 at this point, and you're going to be able to see your graph pretty quickly. So if I picked, let's say we picked a negative 2, a negative 1, 0, 1, and 2. All right, so I'm going to pick those 4 values. I can look at my table real fast. I can find out what those values are. I'm going to get a negative 0.25. I'm going to get a negative 0.5. I'm going to get at 0 a negative 1. And at 1, I'll get a negative 2. And then I'll have a negative 4. And just for grins, I'm going to put a 3 down because you're going to see that jumping up pretty fast. That's an 8. Negative 8 on a 3. Okay, so you can see these values are real small, gradually, changing, and then they start to drastically change. All right? And if you think about this, if we just plugged in, okay, we're going to plug in a negative 2. Well, it's 2 to the negative 2. Means that we flip the 2 over, so we have 1/2, and then we have to square 1/2, which means 1/4, and that's what we get here, negative 1/4. If this was 0, we put a 0 up there. What is a negative 2 to the 0? Well, it's 2 to the 0 is 1. And then we apply the negative, so we have a negative 1. And then we put a 2 to the first power is just 2. We put the negative sign in front of that, so it's a negative 2. So you could actually work these out yourself if you wanted to. The calculator just makes it a little bit easier for us to do. But create your table, and then let's create the graph itself. We notice the graph is going to look something like this right here. So I'm going to actually move my origin kind of off center just to give me more room to draw the graph of the function itself. I know at negative 2, I'm at negative 0.25. I know that at negative 1, I'm at negative 1/2. At 0, I'm at negative 1. At 1, I'm at a negative 2. And then I go negative 4. And then I go negative 8, which is way down here. And so you can see what the graph is doing here. I am coming from way down there. Okay. And then remember, I'm going to have this asymptote at the x-axis. So I'm going to get really close to that, but I'm never going to touch it. I'm just going to stay right beside it and just gradually get closer, but never touch it. Okay? So that's my graph, and that should be what this graph looks like here. All right? And that's all we're doing on these 4 here. We're just looking at it on the calculator, grabbing some point values, and graphing it ourselves on to the grids that we have. On number 9, we're going to do the same thing. We're going to put this in the calculator. Y equals, I'm going to clear out the other function. I'm going to put 2, parentheses, 1 divided by 4, raised to the x value. And I'm going to graph it. Give me an idea of what we're looking at here. Okay. Once this is graphed, then I'm going to look at the table and start building a table of values to plot some points. Okay, I know it's going to look something like this, so I'm going to draw my origin here kind of off center again, just to give me room to draw the rest of the graph so we can really see it. All right, so there's my origin. Here's my table of values that I'm going to create. Okay, so I go to second, graph, and that takes me to the table. Be sure you're following along with the calculator so you're knowing what buttons to push to get to these points. I'm going to go down here to, let's go to negative 2 again. We'll start at negative 2, negative 1, 0, 1, 2. We'll stop at that point. At negative 2, what's my y value? It's 32. At negative 1, drops down to 8. At 0, it drops down to 2. And then at 1, it's 0.5. At 2, it's 0.125. And you can see at 3 there, it's getting smaller and smaller and smaller. It's going to get smaller, as the graph shows, but it's never going to touch the x-axis. It'll never actually be 0. It's just going to continue to get smaller and smaller and smaller. And you can see that on the graph here if I go down a few more. That's just getting smaller and smaller and smaller and smaller. Okay? All right, so if I graph some of these points here at negative 2, I'm at 32, which is way off the graph. At negative 1, I'm at 8. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm right in there. At 0, I'm at 2. And then 0.5, and then 0.125. So I'm coming from way up here, and then I'm curving in. And again, I'm going to be nearing the asymptote, but not ever touching it. So I'm going to be getting close to the x-axis, but never touching it. And that's what my graph should look like, just like what we had in the calculator. Okay, number 10. On number 10, we're going to do the same thing. And we're going to notice something here that's pretty interesting, and hopefully we'll start to see this in our functions as we move along. But we're going to have 4 raised to the x power. Make sure you arrow over to get out of the exponent field on the calculator. And then we're going to minus 2 from that. Okay? Now, if we just had 4 to the x, I'm going to put, because I have colors on here, I'm going to show you what 4 raised to the x power is. And just for demonstration purposes, I'm going to put 4 raised to the x power plus 2 is. Okay, so I've got 3 different graphs here, and they're 3 different colors, so they're going to show all these when I graph them. I want you to look at something. The main thing I want to show you here is just what does that 2 sitting out there, or negative 2, do to the graph? What does it do to the graphs? The main function, really, the base function, is that 4 to the x. The negative 2, if you notice, the red one is without the 2. Where is it? It's right on the x-axis. The x-axis is the asymptote. The negative 2 did what? How far did it move the graph? Moved it down 2 spaces. And then if I said, well, plus 2, what did it do? It moved it up 2 spaces. So that value is very similar, in fact almost identical to our b, or our y-intercept value in a linear equation. And we know that that also told us where that graph was going to cross the y-axis. So that 2 out here, the negative 2 in this case, is saying that, well, we're going to move it in the y direction somewhere, either up or down. If there's nothing there, then it doesn't move it in the y direction anywhere. It's just in the parent function location. This case would be right on the x-axis. So you're going to see this graph. The blue one is actually our graph that we're looking for. Let's go into y equals, and we'll clear out these other 2 so that we just have the 1. And let's go back to our table and grab a few values. Okay, so x, f of x. We know our graph is going to be kind of below the x-axis. I'm going to go ahead and just leave this pretty close to centered for now. Okay, and then let's go ahead and we'll do a negative, let's do a negative 2. Negative 1, 0, 1, and 2. I don't think 2 is going to fit on the graph, but we'll give us an idea. Negative 2 is going to be a negative 1.938. What is it getting closer to at this point? It's getting closer to that negative 2 value. That negative 2 is our asymptote value for y, right? Y equal a negative 2 is the line it's approaching. All right, and then at negative 1, it's negative 1.75. At 0, it's negative 1. At 1, it's 2. At 2, it's 14. Let's plot some of these points and see if we can make it look like the graph we saw on the calculator. So at negative 2, I have a negative 1.938. At negative 1, it's at negative 1. I'm sorry, it's supposed to be 9.8. I went to 9.938, not 1.938. At negative 1, we are at 1.75, so we're right in there. At this 0, I'm at negative 1. Scratch that one right there. At 1, I'm at a value of 2, and at 2, I'm at 14, which is way, way up here at the top somewhere. So here's my line. I'm getting very close to negative 2. And then I'm curving up drastically, going up in that direction. And you'll see I'm not going to touch negative 2, but I'm almost there. Again, disregarding that 1 point right there. And if we look at our graph, again, we should see very similar looking graph on the calculator. And we do. Okay, last one, number 11 here for 6.3. Let's look at that. I'm going to again go to y equals. I'm going to put this into the y equals spot here. 4 times 1 divided by 2 raised to, and this is an interesting one, but it's not too hard. We can still put it in just like it is, x plus 1. As long as you stay in that exponent position, then you can just plug that in, and you'll get the right graph and the right table values for this as well. Okay? So if we're looking here, we're going to see our graph coming down, and it's getting closer and closer and closer and closer to the x-axis, but not touching it. So let's get our table values, and let's graph this. Again, this one's going to come down here. I'm not really too concerned about the location of the origin, but we'll put it here for now. Let's create our table of values. And we'll start with a -2 when we've got 0.5, I'm sorry, 8. I'm sorry, -2 is 8. -1 is 4. 0 is 2. 1 is 1. 2 is 0.5. And just for grins, 3 is 0.25. So if I'm plotting these points at -2, I'm at 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'd be somewhere in that area right there. -1, I'm at 1, 2, 3, 4. Then I'm at 2, and then 1, and then I'm at 0.5, and then 0.25, and then I'm just getting closer and closer to the x-axis, but never touching it. So my graph looks something like this right here. Okay. Again, getting close to the x-axis, but never touching it, because that is my asymptote. And if I look back at the graph here just to confirm, it does look the same. Okay. That's the end of 6.3 notes, but let's go ahead and flip over and look at 6.4, and we will get through that rather quickly to finish out this lesson on notes. On 6.4, we're just going to talk about exponential growth and decay, and the exponential growth and decay functions. And this is going to be real easy because we already have a pretty good understanding what exponential functions are. Now we're just going to define what direction we're going with these functions. So an exponential function that is an exponential growth is going to be a function value, we'll say f of x or y, okay, that is always increasing exponentially. Okay, so a function value f of x or y that's always increasing exponentially. As x increases, the value is increasing exponentially. Okay, and for this function that we're going to look at, the actual function itself is the actual function that we're going to have itself is going to be y equals a times 1 plus r raised to the t exponent or power. And this is going to have some stipulations too, or conditions, where a is greater than 0 and r is greater than 0 as well. Okay, so a greater than 0, r greater than 0, and this is our function. Now we'll look at our illustrations here in a minute. A is going to be our original amount that they give us to start working with, try to find, maybe our end value, which is our y. R is the rate in decimal form of the change, and t is the amount of time, usually in days, months, or years. They'll specify that. So that's what these kind of stand for. We'll see a little better illustration of that in just a minute. Exponential decay, and just for reference here, when we talked about the savings account and our savings account value changing every year, what kind of function do you think that would be? A growth or decay? If it's increasing every year, that would be a what? Growth. Yeah. A decay function might be where you're taking money out of an account, and it'd have to be exponentially. So you'd be taking money out of an account or making withdrawals from an account exponentially. Or maybe you have a business that is declining, and so your profits are declining exponentially. And obviously not at a steady rate, because then that would be a linear function, but they're declining drastically more and more each year. Okay, so exponential decay is just simply the opposite of this one here. It is a function value where you have f of x or y that's always decreasing exponentially. Exponentially. So again, it's going to have to be not a constant rate of change. It's going to have to be decreasing exponentially. And the formula for that one, or the function that we'll see for that, is going to be y equal to a times, here's the difference, 1 minus r raised to the t. And again, we have some criteria here. This is where a is going to be greater than 0, and r is going to actually be between, oops, I did that wrong. It's supposed to be 1. Between 0 and 1. So r has to be between 0 and 1. A has to be greater than 0 for these functions to be correct. Okay. Let's look at the illustrations that we have down here. And this is going to be pretty easy because we're just going to have to plug the values in and evaluate them. So again, the growth function, the initial amount is the A. The rate is your R, and it's in decimal form. If I gave you 25%, what is the decimal form of 25%? 0.25, correct. All right. T is your time, and this whole section here is your growth factor. You've got your initial amount times your growth factor. Okay, so this portion here is your growth factor. Of course, all of that together is going to equal your final amount. Okay. Again, because this is adding your percentage or your rate, this is your growth. And this one, because you're subtracting the rate or the percentage there, then you're getting less than your original amount. That means you're declining or you're decaying, decreasing in value. Again, the same thing here. Your initial amount is your A. Your rate's also going to be in decimal form here. You've got your T, which is time. This whole thing is now your decay factor. And then your final amount is what all those evaluated, the final answer would be, or final amount would be all those things evaluated together. All right, let's look at some examples, and then we'll be done with 6.4. On extra practice here, we have a two-part word problem here that's not too difficult. It says in 2005, there were 100 rabbits in Polygon Park. The population increased by 11% each year. Okay, so now let's just talk for a second here and gather information for our formula so that we can plug in certain values. What is the initial amount of rabbits in Polygon Park? Our initial amount is supposed to be A, and there were how many? 100. Okay. What is the rate at which they're increasing every year? It's 11%, so we need to change that to decimal form, which will be 0.11. Yes. Okay, now, and then the time they're asking on this first part, or part A. Write an exponential growth function that represents the population T years after 2005. Well, let's just give an example here and play with some numbers and see how we would find that. Let's say it was 2010. How many years is that past 2005? How did you get that? Well, yes, 5 plus 5 equals 10. But if you take 2010 and you subtract the original year, 2005, that gives you the total amount, right? So our function, y is going to equal the initial amount, a, times 1. Now we're talking about growth. So this is 1 plus the rate, 0.11, raised to the power of, remember, whatever year it is, minus 2005, right? So we're talking about t minus 2005. So whatever time it is right now, minus the 2005, that's going to give us the amount of years we need, right? Okay, so that should be your function. Yes? Okay, looking at B, let's apply it. What if it's 2025? Okay, y equals a 1 plus 0.11 raised to 2025 minus 2005. And what was a? 100. So we could actually just replace a with 100, right? So what does this mean? We're going to have y equals 100 times 1 plus 0.11. What's 25 minus the 5? 20 years. Very good. Now, if we do all of those, evaluate all of this, we take 1, add it to 0.11, raise it to the 20th power, multiply it times 100, we get 806.23 something. Can you have 0.23 of a rabbit? Not really. That'd be kind of gross, wouldn't it? You just have a fourth of the rabbit. So we go to the nearest whole, number that we actually could have. In this case, we had to go back down to approximately 806 rabbits. Okay? So at this point here, all we really had to do was just plug these values in to the locations once we found them. All right, let's look at the last few things here. 2, 3, 4, 5. Determine whether this is an exponential growth function, exponential decay function, or neither, and explain. And on the first one, again, they made it easy for us on the x side. They're all increasing by 1. Here, they're increasing by 10, 15, 22.5. The y value is doing what? Increasing or decreasing? Increasing as x is increasing. So because it's increasing, is this growth or decay? Growth. So this is an exponential. I'm going to abbreviate here. Growth. Okay. Y value increasing exponentially. And you could say as x is increasing, but that's kind of understood at this point. Okay, that's the first one. The next one, again, all ones for the x, change in x. Change in y, negative 120, negative 30, negative 7.5. What's happening to the y value? It's getting smaller or decreasing exponentially. It's not a constant rate, is it? No. So this is exponential decay. Exponential decay, and again, the y value is decreasing exponentially. I'm going to abbreviate that too. Why not? Just for sake of space and time. All right. Number 4, we have, again, the x value increasing or changing by 1. The y value decreasing by 10 at every change in value there. At every point, coordinate value they give us is changing by 10 every time. Well, this is going to be a neither. And why is that? Why is this a neither? Yes, it's right. You are correct. It is linear. It's linear because there is a constant rate of change. Okay, because there's a constant rate of change, it's linear. It is not a decay or a growth, and it's because it's not exponential at all. The last one, we are changing by 1, 1, 1. Oops. And here we're changing by 6, then 15, then 37.5. So what is this going to be? Exponential growth. And because we are, the y value again is increasing exponentially. Again, I'll abbreviate that one. Okay, and that concludes our 6.3 and 6.4 notes. Hopefully this will help you guys get started on your practice. You'll have all weekend to work on your practice, and we will work on practice in class on Monday as well. All right, you guys have a great day and a great weekend.